Rotational kinetic energy. We've already seen kinetic energy, so now we look at rotational kinetic energy. The units will still be joules. So consider a very light X cross made of light material but very rigid, and we have four masses, and let's assume that they are all equal, attached at the ends, and this is spinning about the vertical axis at the center with some angular velocity omega, radians per second. So this mass m1 is going to be moving at that instant of time in this direction with the velocity v, and this will also be moving with the same velocity v but in this direction. So they'll all be going in the forward direction with the same value of velocity. Now if we consider one of these, for example this one, what is its kinetic energy at this instant of time? So its kinetic energy is going to be half m, the mass of that object, times v squared. And well, there are four of these, so the kinetic energy of this one is also going to be the same because the mass is the same and the v is the same. So the total kinetic energy of all four is going to be 4 times half mv squared. Now we know that v equals r omega, which means omega is v over r. And so if we replace, well, yes, so if we replace v with r omega, this becomes half and m and r square omega square 4. Now we can rewrite the 4 over here and remove it from here. So this mr square is the moment of inertia of this mass about this axis, and this distance is r. And so that's the moment of inertia of the mass m1. And the whole thing, 4 times mr square, will be the moment of inertia of all four of them, of this all four masses about this axis. And so this can be replaced with the moment of inertia, and so the kinetic energy is half, this becomes the moment of inertia of this system, omega square, and that is equal, that is what we call the rotational kinetic energy. And to differentiate it with the linear, we can call this the linear or the translational kinetic energy. Now if we do a small example, let's assume that we have a cross which is the same as what we had in an earlier lecture. So we had this x, which was 0.5 meters here and 0.3 meters here, and these were 4 kilogram, 4 and 2 and 2 kilograms, spinning about the axis a prime. So this thing was spinning like this, and we found that this 4 mi/ri square gave us 0.72 kilogram meter squared. So if we have the same thing and it's spinning with a certain omega, let's say the omega is 4 radians per second, and the moment of inertia is 0.72 kilogram meter square. So we're solving for this spinning at 4 radians per second square, 4 radians per second. Then the rotational kinetic energy, which we can write it like this, is half I omega square, will be half 0.72, and omega is 4 radians per second square, and this will give us 5.76 joules. Now if we want to find the moment of the rotational kinetic energy about the axis BB, well, we'll just replace the moment of inertia with whatever we have for this particular axis spinning this way. And that's 1, so we can just replace here, we can just replace this with 1. Now let's go to another example. And And this time we'll first solve it for the case where we have a simple string. So let's suppose we have a support with a pin here, and we tie a string to it, and we attach a weight over here of mass m. This distance is r, and we're holding it here, and then we let it go. At that point, if we let it go, it's going to swing downwards, and it's going to keep going like this, and it becomes a pendulum. So as we let it go, it's going to swing, and it's going to go like this, and we want to find its velocity when it's at the lowest point. What is its v over here, given that v initial is 0, that's v final. So we can solve this by using the delta k plus delta ug, and there's no spring, no external work, no friction, so that equals 0. So it's going to be k final, which is here. This is the final position, and that's the initial position. K final minus k initial plus ug final minus ug initial equals 0. And if we set the x-axis here and the y-axis here, then this is y final is 0, and the y initial is r. So this will become half m v square, v final square, minus the initial v is 0, so it's going to be 0, plus mg. This simply becomes y final minus y initial, and so we get half m v final square, and v final minus v initial is going to be 0 minus r. So 0 minus r is going to be negative mgr is 0. And we can move the this thing on the other side. We can also cancel this out. So we'll have vf equals gr times 2 gr times 2 and a square root. So it's going to be 2gr square root. That's the speed with which it's going to be moving when it's at the lowest point. We can also use the same analysis to find the speed at any other position. All we need is the new value of yf. This is going to be the new yf if we want to find the speed when it's crossing this point. So when you want to find the speed when it's crossing this point, we need this value of yf. Now we would like to solve the same problem using the rotational kinetic energy, but it's hard to think that a string and a mass becomes a rigid body. So let's change the problem slightly. The problem is still the same, but we'll think of it differently. So we have a light stick. It's a rigid massless stick. At the end of this we have our mass m. So it's the same mass as here. The stick is massless, just like the string was massless, but now it's a rigid. So it becomes a rigid body. And this, once we release it from here, is going to swing downwards and go up here, and we want to find it when it's at the lowest point. So now we use a rigid body thing, and it's rotating rigid body about that point. So we use this equation, and we'll say the delta k plus delta ug, no spring, no external work, no friction, 0. The delta k is going to be k final rotational minus k initial rotational plus m, well, that's the ug final minus ug initial. Okay, so the rotational kinetic energy final is going to be half I omega final square minus half I omega initial square, and that's going to be mg y final minus y initial. Now, because we released this from rest here, we'll do the same thing here. Vi is 0 and omega I is also 0, and so this is 0. And we know that we can set up the x-axis here and the y-axis along here. So this will be y initial. So where is y final? Okay, this is massless, so the y final is here. And so we'll have y final minus y initial is the same as the length of this thing, which we can again keep as r. Now, the moment of inertia of a point mass at this distance is mr square, and the stick is massless, so it contributes nothing to the moment of inertia. So this is going to be half mr square omega final square equals mg, and y final is 0, y initial is r, because this is going to be r, mgr. The m's can cancel out, one of the r's can cancel out, and omega is going to be v over r, so we can write it as half r v square over r square is g. One of the r's will cancel, and v square becomes equals to 2gr, and so v is 2gr, which is the same as before. So whether we go by this route or this, we should get the same answer, and we do get the same answer. Now let's try something a little bit more involved, and this one is a rigid body, a pin, but now it's like a meter stick, and there's no mass at the end. So we have a meter stick, and we let it go. At this point, the length is L, and initial omega is 0, initial V is 0. It would have a mass m, and we want to find the speed with which it is moving when it crosses. It's going to go like that. So what is the speed at this point? Now the center of mass of the stick is going to be here, which is going to be here. That's L, so this is going to be L by 2. Now we write our equation. Delta K plus delta UG is 0. So the delta K is now going to be half I omega final square minus half I omega initial square. And this is going to be mg y final minus y initial equals 0. Omega initial is 0, so that can go away. And we can set our x here and the y along here. So the y initial is this length, that's L. But what is y final? And we're going to find y final for the potential energy. So if you look at this example, this is y equal to 0, and that's the y. If you have a stick like this, and this height is h, then the potential energy here is going to be mgh. Now if you turn the stick and make it like this, the center of mass is still here. What's the potential energy of this stick? There are some parts which are below mgh, some are above mgh, but an object behaves as if its mass is at the center of mass, so it's still going to be mgh. So it's the center, the height to the center. So we need this height. So this is our y final. And so we'll use that in here, and we'll write it as half I. The moment of inertia for stick at one end is 1/3 ml square omega final, which we can keep as omega final for now, and it's initially 0, plus mg, and y final is L by 2, y initial is L, so it's going to be mg, y final is L by 2, and y initial is L, that's minus mg L by 2. Okay, so put a minus here. And then we can cancel out the m, and we can cancel out the 2, we can cancel out one of these l's, and there's a square here, so omega final square becomes g and 3 over L, and so omega final is square root of 3g over L. That becomes the angular speed when it crosses this point. And now we want to find the velocity here, or we can find the velocity here. So the velocity at this point is going to be v center of mass, and the velocity here is going to be at well, we can call it at the end of this stick. So first we'll rewrite this equation in terms of v, and so we use again v equals r omega, or omega is v over r. So this becomes v over r equals 3g over L, and therefore v at any value of r is r 3g over L. And we can write that also as r square 3g over L, and take the r inside. Now the v at the center of mass, so we want to find the v here. The r is going to be this distance, which is L by 2. So that's going to be v at L by 2. So r becomes L by 2. So we replace r with L by 2. It becomes L squared by 4, because it's squared, 3g over L. The L will cancel, it becomes 3g L over 4 square root. This becomes the velocity at that point. Now the velocity at the end is going to be v at L, and so this becomes L square 3g over L becomes 3gl. This is 3gl by 4, so this is half of this value, which seems reasonable. Now to extend this a little bit further, what would be the speed, or let's just find omega when it is at that point at some angle theta. Okay, so what is the angular speed? Here the angular speed is 0. What's the angular speed at any angle theta? We've got the omega at that point. Now we want to find it at any value theta. So in that case, we'll write the same equation. This stays the same. V final becomes here. This becomes V final. And this is the thing that's going to change. The y initial will remain the same. The y final will now be here. So this is now y final when it's over here. And that's, well, the center is going to be slightly to the left. It's not going to be under it because it's swinging. Okay, so this is going to be y final. So that becomes the problem to solve. Here's our stick. Here's the center of the stick. This is the angle theta. This is the center of mass that has become a little bit to the left. This distance is what we're looking for. This is y initial, this is y final, and this distance is h. This is L by 2. This is delta delta y. And we know that delta y over L is sine theta, and therefore delta y is L sine theta. So we can replace this delta y with L sine theta. So this becomes L sine theta, and after this substitution we get from here we get half I omega final square minus mg and L sine theta is 0. All I've done is I replaced this with L sine theta. And then on simplification, which can be done rather straightforwardly, we get omega final is 3g over L, which we had over here, times a sine theta and a square root. So that becomes the angular speed, and the linear speed can also be found by using v equals r omega. We can find, or omega is v over r, we can find the linear speed at any point as it's falling down.